Chapter 5, and today we're going to focus on deriving frame element equations. And as usual, before we jump into the equations, we need to understand what is a frame element. And you probably heard the word, and maybe civil engineers use frames a lot, but we also do mechanical and aerospace, because many structures are composed of frames. Okay, so many structures are composed of frames. And with that being said, we need to define what is a frame. We need to define what is a frame. So a rigid plane frame, and we're going to focus today on plane frame elements, is defined as a series of beam elements rigidly connected to each other and what I mean here by rigidly connected to each other, that is the original angle between elements remains the same after deformation. And having mentioned angles here will tell us that if we have more than one element connected together at an angle, then the loads are no longer just transverse to the axis of the beam. So we're not just going to have a transverse displacement, but we're going to have a component in the transverse direction as well as another component in the axial direction. When the connections are rigid, the moments are transmitted from element to element at the joints. So we can say frame elements are subject to both transverse and axial forces as well as moments. A frame element in plane will have 3 nodal degrees of freedom, U, V, and phi. So if I want to look at a frame element, in its simplest form that has 2 nodes, node 1 and node 2. If I'm looking at the local axis, x prime, y prime, the equations for the frame element are going to depend on E, I, and A. And if I am to show the 3 nodal degrees of freedom, we're going to have translation along the axis of the member. I'm going to call this 1. Translation in the transverse direction, 2. And a rotation, 3. I have 2 nodes. So on at the second node, I'm going to have a 4, a 5, and a 6. So 2 nodes, 3 degrees of freedom per node. That would give us 6 degrees of freedom total. Now, in chapter 3, we learned about bar element. That also had 2 degrees, had 2 nodes at 1 and 2, and had 1 degree of freedom per node. If this is x prime, we had 1 and 2. In chapter 4, we learned about a beam element. And we looked at an element with 2 nodes, 1 and 2, x prime, y prime. And the beam element that we derived the equations for had 2 degrees of freedom per node. Translation, 1. Rotation, 2. And at the second node, we had also a transverse translation, 3, and a rotation, 4. Now, looking carefully at these 2 elements, if I combine these 2 elements, I will get the 6 degrees of freedom that the frame element has. So what we're going to use is we're going to use the element equations for a bar element, element equations for a beam element that we've already derived, and superimpose them together to find the element equation of a frame element. The frame element from a mechanics point of view, is subject to a bending, shear due to bending, as well as axial forces. So that tells you that when I superimpose a bar and a beam, that will give me the behavior of a beam element. So what I'm going to do here is I'm going to write the element stiffness equations for the bar element with respect to x prime, the local axis, right? So we had the F1 and F2 based on this notation is equal to AE over L multiplied by a 1 minus 1 minus 1 and 1 multiplied by U1 and U2. The element stiffness equations for the beam element with respect to the x prime, y prime, or the local axis. Local. We had the F1, we call it F1y, and actually maybe we can make this F1x and F2x. F1y, yeah, sorry. M2, F3y, and M4 equal to EI over L cubed. And we had here a 12, 6L minus 12, 6L, 6L, 4L squared, minus 6L, 2L squared, minus 12, minus 6L, 12, minus 6L, 6L, 2L squared, minus 6L and 4L squared, multiplied by the V1, V2, V3, and V4.
So in the past, we were writing it like V1, V1, V2, V2. Are we changing the notation because it's going to make what we're about to do easier?
We wrote it as V1, V1, V2, and V2.
Yeah.
Yes, I am actually going to change even the notation here before we assemble them together. Okay. So what I'm going to do now is I'm going to write the corresponding frame degree of freedom next to each of these equations. So I'm going to come here and I'm looking at my frame element. And even though I call this 1, here it is also 1. So I have here 1, degree of freedom 1. And 2 would correspond to 4. So you see 2 and 4 corresponding to each other. So I'm going to put 4. Okay. I'm going to do the same with the beam element as it compares to the frame. So my 1 corresponded to 2 here. So I'm going to write this as 2. And my 2 on the beam element corresponds to 3. So I'm going to put 3. The 3 corresponds to 5. So I'm going to put 5. And the 4 corresponds to 6. So I'm going to put 6. But yes, I would like to go back and keep it simple. And for one, use V1. For two, use, U1, V1, and V1. So I would like to do that as we move into the frame. Yeah, which really, if we are using this red notation, I don't mind keeping it as 1 and 1. And here we can keep it 2, 2, and 2, and 2. And you can use the red notation, all right? That would make it consistent. So if I am to superimpose these two together, I can write superimpose or really add the element stiffness equations of a bar element and a beam element in matrix form. And I still want to emphasize that this is with respect to the x prime, y prime local axis. And when we are going to write these, we are going to go like 1, 2, 3, 4, 5, 6 in terms of the degrees of freedom for the frame elements, where 1 corresponds to a U1, 2 corresponds to V1, and 3 correspond to V1. 4 would correspond to U2, and 5 would correspond to V2, and 6 would correspond to V2. Right? So these are the displacements. Corresponding to these displacements, we are going to have the nodal forces as F1x, F1y, M1, F2x, F2y, and M2. So as you can see here, this stiffness matrix is going to be a 6 by 6 because we have 6 degrees of freedom. Of course, this is a 6 by 1, and this is a 6 by 1. And I am going to let C1 be equal to AE over L, and C2 be equal to EI over L cubed. And we're going to use these for simplification. So I'm going to get a C1 here. I'm going to get a 0 and a 0, and then a minus C1, a 0 and a 0. And corresponding to F2x, I'm going to get a minus C1 here, 0, 0, and C1, 0, 0. So really, these are the two equations of the bar element, where we had AE over L. So I have here the AE over L, and we put it here These are the two equations. Next, we are going to take the equations from the beam element. So we can say that here, corresponding in the first column, we're going to get zeros and zeros, 0 and 0, as well as the fourth column, we're going to get these zeros. So the remaining here are going to be coming from the 4x4. So I'm going to write it using C2. So I'm going to have here 12 C2. I'm going to have 6 C2L. 6 C2L symmetry. And here I'm going to have a 4 C2L squared. And this is going to be repeated here for this 4x4. So I'm going to get a 12 C2, 6 C2L, minus 6 C2L, and 4 C2L squared. Here I'm going to get a minus 12 C2 and a 6 C2L, minus 6 C2L, and 2 C2L squared. And this is going to be repeated here, minus 12 C2, 6 C2L, minus 6 C2L. I'm sorry, this is a plus. Yeah, this is going to be plus and plus. This is going to be minus. So this is minus and this is plus. And 2 C2L. Here I have 6 C2L minus 6 C2L. Here it's the minus 6 C2L and plus 6 C2L.
You have another 6 C2L minus 6 C2L.
2 C2L squared. Let's check. Here is my diagonal, right? And it should be symmetric.
Bottom, second bottom from the bottom all the way to the right. The 6 C2L, should that not be negative?
No, it is negative. It is negative.
Yeah, negative 1.
Oh, so here this is positive. This is also missing a negative sign.
Yeah, that was good.
So when we did this, we got to get the frame element stiffness equations. Again, with respect to x prime, y prime. So now we want to go from the local axis to the global axis. That's the next step.